Hello, everyone. So today I'll talk about the second session. So I will talk about the basic properties of water. Um, so kind of introducing up from my last video, I'll talk about some of the properties of water on different aspects. First properties, I'll talk about some atomic ones. Second property, the molecular ones, and then the third property, which is kind of accumulation of the atomic and the molecular, which kind of brings down to our our fourth non-covalent interaction called the hydrophobic effect. All right, so let's get started. Mhm. All right, so let's start with the atomic properties of water. Atomic properties of water. Atomic properties. Now, um, like you've seen for example, like carbonea from my last video, for example, you may notice that the water is also a polar molecule. What that means is that so that is our oxygen, and then we have this hydrogen. Hydrogen. There are two of them bonded together. Oh, bonded together. The reason why the water is polar is because there is a difference in electronegativity between the oxygen atom and the hydrogen atom, which means that since oxygen is more electronegative, if you watch my previous video than the hydrogen, there is this disproportional distribution of electrons across the entire molecule or between the atoms. So there'll be more actually electron density localized in the oxygen, whereas in the hydrogen there'll be a less electron density. But note that since there are two hydrogen with one oxygen, we see this two bipolarity going on between the two hydrogen atoms and two hydrogen atoms and one oxygen atom. So you'll have this directional polarity across the one single water molecule. Now, so why are we even talking about this in the first place? Is that this molecular polarity actually uh, and the overall existence of this dipole moment, the arrows I just drew. Dipole moment. Um, it actually influences how this water interacts with other biomolecules. I'm sure you guys have heard about how our body is composed of 70% of water, which means that since there's so much water in our body, or even other type of animals starting from bacteria, is that all our biomolecules, including lipids, amino acids, carbohydrates, their structure and their ultimate functions are even governed by how those specific biomolecules interact with the water. Oh, and that's what we're going to talk about from my subsequent um, lecture. Okay, so let's first draw out the water and in more of a microscopic view. So I'll draw some of the lone pairs and some of the bonding orbitals that we might be interested in looking at. So for example, uh, so drawing the water molecule again. We have that. Oxygen should be a little bit bigger. Okay, that's good. All right, so uh, the bonding orbitals, which are just an orbital that is formed between the sigma bonds between the oxygen and the hydrogen, this is what we call the bonding orbitals. Orbitals. And it is important to note that the reason why the water it is not linear like carbon dioxide, but has this angle between the oxygen and the hydrogen atom is that I'm sure you guys has heard of the reason why that is the case. So for example, there are some theories about the let's see, Vesper. theory is that the non-bonding or non-bonding electron pairs in the oxygen atom repel each other. So, for example, there will be non-bonding pairs over here and non-bonding pairs over here. Is that since those are two electrons and they have a same negative charge, what they'll do is they'll try to repel against each other. So that's why you guys may have heard that heard that there's a reason why there is this slanted angle between the oxygen and the hydrogen atom. Uh, but if you try to explain that same phenomena in terms of molecules in orbital theory, is that just like there's a bonding orbitals can be described as sigma orbitals, you can express these two non-bonding pairs as a non-bonding orbitals at the same time. So if you redraw this oxygen this water atom, water molecule, sorry, is that these two are essentially two separate orbitals called the non-bonding orbitals. Because of that, since these orbitals they occupy a similar just separate volumes in a 3D space, what happens is that in order to kind of maximize the angle between not only these two but also the rest of the bonding orbitals that is formed between the oxygen and hydrogen, is that what happens is that these four orbitals they form a tetrahedral. So just like the methane that has formed stage 4, stage 3, just like to tetrahedral to maximize the dispersion of the electron across the non-bonding and bonding orbitals, that will have this tetrahedral form. And by reason and because we only care about these bonding pairs or these bonding orbitals, we kind of neglect the fact about the existence of this non-bonding orbitals. So that's why we only care about just the bonds. And then, but it is important to note that the reason why this angle is formed, it is because of this unseen or the unseen orbitals, non-bonding orbitals that causes such angular distortion. Let me just finish up in that. Yeah, distortions. Great. Okay. So as a summary, okay. So summary. So water has as a molecular label. One second is that there is because there is a difference in electronegativity, we see a partial charges delta positive in the hydrogen and delta negative in the oxygen atom of the water molecule exist. In water. And the last point is that this non-bonding orbitals occupy defined space location in space. No, because forms a tetrahedral structure between the bonding orbitals and non-bonding orbitals. Okay. All right. So that is that. Now, I would like to mention the second property of water, which is just the molecular properties. This is more of a intramolecular property across the model molecules. H2O. Now, the reason why I bring this up is that because there is a dipole moment and difference in electronegativity and the existence of partial charges is that the water molecules can and obviously undergo hydrogen bonding. So let me just kind of visualize how that works. Okay, so for example, if this is the center water molecule, and then we know there is this dipole moment of the charge. The one water molecule can actually go uh, can interact with can have 4 hydrogen bond. So I'm just gonna show you how that is the case. So let's label this water molecule number 1. So that's a standard water molecule, and then we have this the separate other water molecules because it's kind of floating about, and we have another one it's kind of floating about like that. And then we can also have another one floating around like that, and another one just like that. So one water molecule can actually interact or actually have form 4 hydrogen bonding pairs. So for example, it's like that, because delta positive, that's also delta positive, and for the other separate water molecules, so that is delta negative. So you have delta positive and delta negative interact to form the attraction, which is a hydrogen bonding. You see the same mechanism going on over here. Positive. Now, for this oxygen, since it has two lone pairs, you can actually go through 2 hydrogen bonding at the same time. What that means is that you have a delta negative over here, one delta negative over here, and one delta negative over here can oh, sorry, I made a huge mistake. My apologies. Yeah, sorry about that. So since it's delta negative over here, it can interact with the 2 hydrogen molecules by one of them interacting with the other partial positive hydrogen ion of a one water molecule, and the other with the separate hydrogen atom of the another water molecule. So essentially, one water molecule can have can interact or have form of 4 total hydrogen bonding, just like that. So let's call it 0. Yeah. And then just to kind of reiterate, the reason why is that the oxygen can undergo 2 H bonds by having 2 lone pairs. So that is the key to why this is the case. Okay. All right. Moving on. Okay. So now I'll just want to talk about some of the macro properties of water. So I just want to kind of differentiate between the properties of water when it is in solid phase versus when it is in a liquid phase. So ice versus water. I mean that is essentially liquid. So I think it's pretty self-evident. Okay, so let's first talk about ice. Ice cube, ice baby, ice. All right. Since ice is a solid form, it is actually more stable. More stable by forming this like lattice structure. So what lattice structure is that for example, since ice is a solid state, it is all the water molecules, they're kind of stacked together, which means all this the distance between the water molecules they're pretty not only rigid, so that the distance they don't change over time, because it's just all state, but they have this organized fashion of creating this rectangular, even like a. But if you look at closely in the uh, when you study like specific intermolecular organization, they have each the water molecules in the ice, they form a six-member ring, or maybe not a ring, but more of a this chain. And this chain is formed by, surprise, surprise, hydrogen bond. So that is the key. One point to note is that so I know there's a hydrogen bond going on with the liquid phase as well, but just to make sure that the this intramolecular hydrogen bond for the ice state specifically is very rigid, and since it is not fluid, the I guess the location of the bond relative to each of the molecules, they're very they're stagnant. But uh, and no movement of H2O molecules. Okay, now let's move on to the liquid phase, which is the water. Right, liquid. Okay, let's see. Um, since water is more fluid, if ice, it's just like that, and water is just like water is more like fluid, kind of moving around. It means that it loses that rigid structure that was specific to ice, which means that there is actually a loss of hydrogen bond. And how many is lost? It's about 15%. Compared to 15% compared to the ice state or solid state. That this also entails or implies that you don't see the stable six-member chain is lost. However, there is this I guess on a positive note, like a silver lining is that because there is this because there's a loss in the stable six-member chain or in the rigid structure, is that the movement of water molecules are just ignore the just the hydrogen the color of the hydrogen, the oxygen, is that the movement of the water molecules, they're very dynamic. So so at one time point this water molecule over here can interact or form a hydrogen bond with this one, and then sometime at the second time point, this water molecule can get closer to this water molecule over here, and then it can then start to form another new hydrogen bond and break this old one. So there's a lot of interchangeability or changes in the hydrogen bond, not only in strength but also this direction, or the number of hydrogen bonds that happens across different time points. So one point to note is that the H bond formation and then destruction, it is very dynamic. It's very dynamic. Very dynamic across. Each time point. So this is a key. Now, why am one of the application or I guess the consequences by having this having hydrogen bond is that it can actually, because of there is a extra strong attraction, in addition to some van der Waals that I mentioned in my previous lecture, is that it actually increases the boiling point of a selection molecule. So I'll make a little chart that kind of does like maybe you can kind of do a cross comparison that affects the boiling points. So I'll let you know molecule, boiling point, boiling point. and I guess the molecular weight, and I guess the presence of a hydrogen bond. Okay. Okay. So, for example, let's consider a molecule CH3. CH3. So that is methane. The molecular weight is about 16, and then its boiling point is about 164. However, water, on the other hand, it has a molecular weight of 18, which is pretty similar to the methane, but it has a boiling point of 100. Sorry, not 1,000, 100. Now, why is this the case? So actually, the boiling point, um, it is um um it is proportional to your molecular weight. But we noticed that the molecular weight between the CH3 and the H2O, they're pretty similar. And the reason why that causes such big discrepancy in the boiling point is because the presence of a hydrogen bond that is specific to water. The reason why I say that is that for stage three, there is the molecule itself is quite nonpolar, so there is no any there's no existing dipole moment. Whereas like H2O, like I showed you guys before, it has the dipole moment that causes it kind of enables the water to go through hydrogen bonding, and because it takes extra energy to kind of break the bond between the molecules, just like this one, that's why it increased the boiling point dramatically. So that kind of shows that kind of significant emphasizes the how important hydrogen bonding is in terms of strengthening the bond between molecules. Okay. So now I would like to talk about the hydrophobic effect, which is the last agenda for today's lecture. Hydrophobic effect. Now, hydrophobic effect is actually not. It is obviously not a covalent bond, and it's really hard to determine or kind of characterize hydrophobic effect as a non-covalent bond, because it's not really a bond, but it's more of a phenomena that is caused by, I guess, the favorability of the water molecules that want to kind of clump together, whereas all the non-polar molecules, they want to clump together, and then that causes separation between the two molecules. The most common example of hydrophobic effect is that if we have maybe you have just like for some reason you have a vegetable oil, and then you decide to kind of pour water in. I don't know why would anybody would do this, but if you shake it, initially there will be a lot of just mixture going on, but if you wait long enough, there is a clear separation between the water and the I guess the oil layer. So even though you guys never done well this, I don't know why would anybody do that, but I think just kind of seeing the separate or expecting the separation of oil and water, I think that's pretty self-evident. And then I'll try to explain that why this happens by kind of including some of the properties that I've talked about, including the hydrogen bonding. So um, for example, okay, so we have this water tank. Okay. Okay. um Because I'm lazy, I didn't draw the specific atoms of the water molecules, but all those dots I'm drawing right now, those are the water molecules. I mean, yeah, atoms of the water. I mean, yeah, the water molecules. One point to note, if you look at this figure, is that the water molecules. If you look closely, if you kind of zoom in, what happens is that on the surface. Oh, by the way, this is just for example, a lipid. So like the oil, like I just mentioned. In the aqueous or just water solution. So anyways, if you zoom that little this periphery of I guess the lipid water boundary, what you see is that first there's this big surface or I guess lipid, and then the periphery of that lipid is that just all these water molecules. They form this chain of hydrogen bonding. So this chain kind of extends all around the I guess the periphery of the lipid, so that one of the properties you can see observe from here is that water molecules become ordered, ordered and interacting with nonpolar solute. Here, e.g., lipid. Now, okay. Second property you can observe is that sometimes if initially if you leave the maybe lipid droplets like that, and then and just like the figure above, we have this water molecule surrounding lipids. If you wait long enough, or for example, this is the initial. We need, let's just consider the first state. The minute after you shook the mixture of water and vegetable oil, and then you will see that after a few minutes, there is this clear separation of oil and water. So that can be described as that. And then this entire thing is just lipid. And then the outside is just the water solution. And then just like the last time, all this part are just the water molecules forming a chain. Yeah, just disregard my hand forming a chain. Now, one biggest observation you can make from this is that first, the nonpolar solutes can minimize 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 the solute water interaction by interacting with each other. So what this observation means is that if you look to the figure to the left, there is actually a lot of interaction going on between the surface of the lipid and then surface of the lipid and also the surrounding hydrogen molecules. So all of these interactions are the ones I'm talking right now. But later on, the hydrophobic interaction kind of favors that minimizing I guess minimizing the number of interactions formed between the lipid and the surrounding water molecules. So that's what happens is that this by kind of clumping to by the lipids kind of clumping together, the nonpolar solids clumping together, is that it minimizes the number of interactions between the total lipid as you see over here and the surrounding water molecules. So that is a reason why uh, uh, there is this clear distinction, or I guess the clear segregation between the nonpolar solutes, the vegetable oil, and the water. But it really doesn't really answer the reason about why this happens in the first place, right? I mean, yeah, sure, it makes sense. Or I guess everything I've said so far, they're just observation, but they don't really explain the reason why this is the case. So in my next lecture, for my lecture 3, I'll explain the reasoning behind or mechanism on why this happens by kind of introducing a new concept of thermodynamics.